In this lesson, we will learn about the law of conservation of mass, and the law of definite proportions. We will also do a simple experiment to test these laws. The law of conservation of mass was developed by French chemist Antoine Lavoisier in 1775. The law states that the mass of the reactants in a chemical reaction must equal the mass of the products. For example, suppose we have a chemical reaction between compound A and B, which leads to three products, C, D, and E. If the law of conservation of mass is true, then the mass of compound A plus the mass of compound B must equal the total mass of the products C, D, and E. In 1799, another French chemist, Joseph Louis Proust, developed the law of definite proportions. The law of definite proportions states that a pure chemical compound always contains the same elements in the same proportion by mass. Let's use water as an example. The molecule of water always contains 2 atoms of hydrogen, and 1 atom of oxygen. Water has an atomic mass of 1, and oxygen an atomic mass of 16. The total mass of the water molecule is therefore 2 plus 16 for a total mass of 18. The proportion of the hydrogen mass in water will always be the ratio of 2 to 18, and oxygen will always be the ratio of 16 to 18. Now let us apply and test the two laws by using an acid-base reaction as an example. There are 3 major definitions of an acid, and research scientists today still use these definitions depending on the type of reaction they are investigating. The first, and most commonly used definition was reported by Svante Arrhenius in 1884. His definition states that an acid is a compound that increases the concentration of hydronium ions. In 1923, Bronsted and Lowry defined an acid as a compound that donates protons, which are hydrogen ions. This theory took the Arrhenius definition one step further, since a substance no longer needed to increase hydrogen or hydronium ions in order to be classified as an acid. The third definition is different than the other two in that it does not invoke hydrogen. This definition, which was proposed by Gilbert Lewis, also in 1923, states that an acid is a compound that accepts an electron pair. Let us look at some examples of acids that fit the 3 definitions. An example of an acid by the Arrhenius definition is sulfuric acid. When it is dissolved in water, sulfuric acid produces a high concentration of hydronium ions, which have the formula H3O+. Hydrochloric acid is an example of an acid by the Bronsted definition because it donates protons. When it reacts with ammonia, NH3, the hydrogen becomes attached to the nitrogen atom to form the ammonium ion, designated as NH4+. Boron trifluoride, which does not have any hydrogen atoms, is called a Lewis acid because it can accept a pair of electrons. When it reacts with ammonia, it forms a compound that has a covalent bond between the boron and nitrogen atoms as shown in the chemical formula, F3BNH3. The definitions of a base were also developed by Arrhenius, Bronsted, and Lewis. An Arrhenius base increases the concentration of hydroxide ions. A Bronsted base is a compound that accepts protons. A Lewis base is an electron pair donor. An example of an Arrhenius base is sodium hydroxide. When it is dissolved in water, it forms sodium ions and hydroxide ions. Hydroxide ions have the formula OH-. Ammonia is a Bronsted base because it accepts protons. In the reaction with hydrochloric acid, it captures a proton from the acid as shown in this diagram. The product is ammonium chloride, which has the formula NH4Cl. One example of a Lewis base is trimethylamine. A methyl group has the formula CH3. When trimethylamine dissolves in water, an electron pair is transferred from the nitrogen to the oxygen of water to produce a trimethylammonium ion and a hydroxide ion. Now let us do an experiment to demonstrate a common acid and base reaction. The acid we shall use is acetic acid in the form of vinegar. Vinegar is a 3% water solution of acetic acid, which has the formula CH3CO2H. The base we will use is baking soda, which is pure sodium bicarbonate. Sodium bicarbonate has the formula NaHCO3. When the vinegar is added to the baking soda, a very vigorous reaction occurs with formation of bubbles, as shown in the photo.
Let us now look at the reactants and products of this acid-base reaction. Once again, the reactants are acetic acid and sodium bicarbonate. The products are sodium acetate, carbon dioxide gas, and water. We now do an experiment to test the law of conservation of mass. A plastic bottle containing 150 ml of vinegar is placed on a triple beam balance, and weights are added to bring the balance pointer to 0. 5 grams of baking soda are added to the bottle on the balance, and the bottle is quickly capped. An additional weight is added to the balance to bring the balance pointer to 0. The added weight should be 5 grams. Observe that the reaction takes place rapidly, with the formation of carbon dioxide gas bubbles. Note that the balance pointer remains at 0, even after the reaction is complete. Since there is no change in the total mass, the law of conservation of mass is confirmed. After the bubbles stop forming, open the cap quickly, and listen to the sound of the carbon dioxide being released. Now place the cap on the balance pan, and notice that the balance pointer shows that the mass has been reduced. Screw the cap on the bottle, and add enough weight to bring the balance pointer to 0. Now record the value of the added mass. This value should be about equal to the value of the mass of the carbon dioxide produced. We will now do some calculations to show that the law of conservation of mass is indeed confirmed. We start by balancing the chemical equations. According to the law of conservation of mass, the mass of the reactants must equal the mass of the products. A good way to balance a chemical equation is to list the number of atoms of the reactants and the number of atoms of the products. In the list of atoms of the reactants, we see that acetic acid has 2 carbon atoms, 2 oxygen atoms, and 4 hydrogen atoms. Sodium bicarbonate has 1 carbon atom, 3 oxygen atoms, 1 hydrogen atom, and 1 sodium atom. The total number of atoms in the reactants is therefore 3 carbon atoms, 5 oxygen atoms, 5 hydrogen atoms, and 1 sodium atom. In the list of atoms of the products, sodium acetate has 2 carbon atoms, 2 oxygen atoms, 3 hydrogen atoms and 1 sodium atom. Carbon dioxide has 1 carbon atom and 2 oxygen atoms. Water has 2 hydrogen atoms and 1 oxygen atom. The total number of atoms in the products is therefore 3 carbon atoms, 5 oxygen atoms, 5 hydrogen atoms, and 1 sodium atom. Therefore, the number and kind of atoms in the reactants are equal to the number and kind of atoms in the products. Now we will use the law of definite proportions to see if the mass of carbon dioxide produced in our experiment is equal to that calculated by the balanced chemical equation. We start by calculating the mass of acetic acid. The chart on the left shows the atomic masses for the 3 elements, hydrogen, carbon, and oxygen, that make up acetic acid. These values were taken from the periodic table of the elements. The chart on the right shows the total atomic mass for a molecule of acetic acid. Each atomic mass is multiplied by the number of the atoms that make up acetic acid. In this case, there are 4 hydrogen atoms, so the mass of all the hydrogen in the molecule is 4 grams. There are 2 carbon atoms, totaling a mass of 24 grams, and 2 oxygen atoms for a total of 32 grams. Adding all the masses together gives a total mass of 60 grams for the acetic acid molecule. These charts use the same calculations for the second reactant, sodium bicarbonate. The atomic mass of sodium from the periodic table is 23 grams. Following the same procedure that we used for acetic acid, the total mass of the sodium bicarbonate molecule comes to 84 grams. We now use the same calculations for the products of the reaction. These charts show the calculations for the total mass of the sodium acetate molecule. The value adds up to 82 grams. In these charts, we show the same calculations for the total mass of the carbon dioxide molecule. The value adds up to 44 grams. Finally, these charts show the calculations for the total mass of the water molecule produced in the reaction. This value adds up to 18 grams. The balanced chemical equation with these values is shown in these diagrams. We now add the values of the masses for both the reactants and the products. If the reactants we used were 84 grams of sodium bicarbonate, and 60 grams of acetic acid, then we would have produced 44 grams of carbon dioxide. In order to shorten the reaction time in our experiment, we used only 5 grams of sodium bicarbonate, instead of the total mass of 84 grams. Since we used 5 grams of sodium bicarbonate, the proportion of the reactant used is 5 divided by 84, or 5.95%. If we had used 84 grams of sodium bicarbonate, we would have produced 44 grams of carbon dioxide. But since we used only 5 grams of sodium bicarbonate, then by proportion, the amount of carbon dioxide produced would be 5.95% of 44 grams. As shown in this calculation, the amount of carbon dioxide produced in our experiment should be 2.6 grams. What was the value of the mass of carbon dioxide that was measured in our experiment? The amount should be close, but slightly less than 2.6 grams because a small amount of the carbon dioxide produced remains dissolved in the water solution. In summary, a simple acid-base reaction between vinegar and baking soda was used to confirm the law of conservation of mass. The law of definite proportions was used to balance the chemical equation of the acid-base reaction, and to calculate the amount of carbon dioxide produced. This presentation was produced as a public service to help middle school and high school science teachers develop experiments, presentations, and demonstrations that can be used in their classes. More science experiments and demonstrations are available on the Tops of Santa Clara Valley website, www.topsofscv.org. TOPS, Teaching Opportunities for Partners in Science, is a program aimed at stimulating greater interest in science by middle school students.